This is lesson 9 on Karnaugh maps. Now we're going to see that Karnaugh maps are going to make it easy for you to reduce sum of products terms into their minimum form. Let's see how this works. Consider this truth table here, where we have min terms m0, 1, 2, and 3. Suppose the output is 1, 0, 1, 1. Now I can draw this truth table in a different form by drawing a square and labeling the rows as x. This is x is 0, x is 1. And labeling the columns y. So y is 0, y is 1. Then this min term m0, where x is 0, y is 0, is 1. That's that 1. This 0, x is 0, y is 1 is 0. X is 1, y is 0. That's this 1. And this last 1 is over here, where x and y are both 1. So this little square here, it's going to be a Karnaugh map as we'll call it, has the same information as this truth table. Now, I can write the sum of products of this function as the sum of m0 or m2 is m3, you remember. And we'll use a shorthand notation. We'll say sum of 0, 2, and 3. This means min term 0, min term 2, min term 3. So it's these three terms. But remember, we only have a single 0 here. So you remember how we did the product of sums. There'd only be one term in the product of sums, which would be this max term. And what is it? Remember how the max term goes. This would be x or not y. Remember? So we know that the solution f can be written as x or not y, which is sort of the minimum way of writing this. The question is, can we get to here by looking first at these three min terms? And we do it by drawing a circle around adjacent ones in the Karnaugh map. So if we draw a circle around here, then we can draw a circle around these two. Now how does this work? Well, see this circle here, notice it covers both this 0 and a 1. If we move this circle up to here, it would circle both the 0 and 1 of the y. Anytime a circle circles the 0 and a 1, the corresponding variable goes away. In this case, y goes away, and we're left with just whatever we have over here. Because it's a 1, we're just left with x. That's this x here. We OR all the circles together, so this circle covers what? Well, it covers this 0 and a 1, which means this x goes away, and we're just left with this 0, which means we're left with not y. So this circle is x, because the 0, 1 goes away. This circle is just not y, because the 0 and 1 makes the x go away. So that's how it works. Now let's see how it works. Let's actually write out these three min terms. So this is going to be not x and not y, not x and not y, or x and not y, or x and y. So here are the three min terms. Now let's see if we can factor something out using our distributive law. Well, here's a not y and here's a not y, so I could factor that out. But here I have an x and here I have an x. So if I had two copies of this, I could factor them both out. Well, we know that z or z is equal to z, so call this z, for example, and this is z or z is equal to z, so I can just add another copy of x and not y without changing anything. And now, from these two, I can factor out this not y. Let's see what happens. I'll factor out the not y. I'm left with not x or x, ANDed with not y. From these two, let's factor out this x. So the x comes out. I have and not y or y. But what's not x or x equal to? Yeah, that's just equal to 1, and 1 and not y is equal to what? Yeah, so we're just going to get not y. What's not y or y? Again, that's 1, ANDed with x just gives x. So this just reduces to not x, not y, or x. That's just our max term here that we had before. Well, you see how it works now. This circle covers the 0 and the 1 in y. Well, that's this term not y or y, which is equal to 1. That's why it goes away. When you AND it with x, you just left with this x. This circle here covers the 0 and the 1 of x. Well, that's just not x or x. That's equal to 1. That's why it goes away, and we're left with this 0 here, which is not y. So you see how drawing the circles in the Karnaugh maps, you can go directly to here. All right, let's look at a 3-variable K-map. X is still 0 and 1, that's the rows, but now we need y in both y and z. So we'll label y and z here, and we'll label these columns 0, 0. This means y is 0, z is 0. 0, 1, y is 0, z is 1. Now here comes the trick in Karnaugh maps. The third column we have to call 1, 1, not 1, 0, as you would in the truth table. And the reason is that in going from column to column, we can only have one variable here change. So if I go from here to here, both variables change. So I can only change y in going from 0 to 1 here. So the third column is always 1, 1, as y is 1, z is 1. And this column, y is 1, z is 0. Let's take these 4 min terms, 0, 0, 0, 0, 0, 1, 1, 0, 1, 1, 1, 1. How many circles do I need to draw here to cover them all? Yeah, I can do it with 2, this one and this one. Now you might think, gee, you could have done these 2, but you don't need this one, you see, because that would give you 3 circles, and we want to have the minimum number of circles that cover all of the ones. You can circle powers of 2, that is, you can circle 2 that are connected to each other, you can circle 4, you can circle 8. So here we circle these 2 and these 2. Sometimes it's a good idea to start with the outliers like this one and see what you need to cover that one. Start with this outlier, cover these, and then you realize that you don't need this third circle. So let's see how it works. Okay, what's this one going to be? This one covers what? Well, it covers the 0 and the 1 in z. So z goes away. Y is still 0, 0, so we have to keep y. It's going to be a not y. We need to keep this x, so this term here is going to be not x and not y. We just AND those together. So not x and not y is this circle because the z goes away. And then we OR this circle. This circle, what min term is left? We've got x here. What goes away here? The y goes away, we're just left with the z, so we're going to have x and z. And that's it. That's the minimum expression that reduces from these original 4 min terms. Now, we could verify this by writing it all out. Let's write this first min term, not x and not y and not z. That's this one. This next term is not x and not y and z. This one is x and not y and z, x and not y and z, and this one is x and y and z. Okay, what can I factor out from here? What's common here? What's common here is not x and not y. Not x and not y. So I can factor that out. So let's factor that out. I get not x and not y ANDed with not z or z. What's common here that I can factor out? I have an x and a z I can factor out, and I'm left with not y or y. So I'll factor out an x and z, and I'm left with not y or y. But again, what's not z or z? Equal to 1. 1 and this is just going to give you not x and y, or not y or y is equal to 1, ANDed with x and z leaves x and z. So again, you see how the not z or z, that is this 0 and 1 making the z go away. This not y or y, not y or y, is this y, makes the y go away, and you're just left with x and z. Okay, let's try another one. How many circles here? Yeah, there are 2, because I get these 2, but now, remember, I can circle powers of 4, so I can circle all 4 of these. So in this case, what goes away here? Well, what goes away here? Well, the x goes away here, and I'm left with what? Y and not z. Y and not z. If I circle this, what goes away? Yeah, both y and z go away, because here I've circled the zeros and the ones of the y and the zeros and the ones of the z. So y and z both go away, and what am I left with? Only x. So this is or x. Here's another one. How many circles here? Yeah, let's start with the outliers. To get this one, now I can't circle 3, remember, they must be powers of 2, so I can only circle these 2. To get this one, I can only circle those. And what's left? Yeah, I can circle this 2 by 2. Remember, I can circle 4 as long as they're adjacent. So I can circle those. And what are we left with? Well, what's this term? This is not x. What goes away here? Yeah, the z goes away, so I'm left with not x and not y. Not x and not y. What about here? Yeah, the z goes away again, and I'm left with x and y. X and y. And now this circle, what goes away? Yeah, well, the x goes away on this side, and the y goes away here, because we have a 0 and 1. I'm left with just z. Okay, so these 3 terms is what this original 6 Boolean terms reduces to. Okay, how about this one? How many circles? Well, there's one for sure. What about these 2? Well, look. This edge here is really connected to this edge. You can think of this as being wrapped around, because in going from here to here, only z changes. Z goes from 0 to 1 here, you see. Y goes from 0 to 1. Z stays at 0. So these are really connected. We actually draw them this way. So this is like drawing a circle around these 2. So now this term reduces to what? Yeah, just x and z. Notice that the y goes away. So that's just x and z. And what about this one? Yeah, we're just left with not x and not z, because the y goes away. Not x and not z. Okay, how many circles here? Well, here's 4 already. What about these? Should I just circle these? Now remember, this edge is connected to this edge. We want to make the circles as big as possible so we get the fewest number of variables in each term. And so we need to wrap around here like this. So what goes away here? Both x and z. Here we're just left with y. And here, x goes away, and y goes away, and we're left with not z. So this whole thing is y or not z. Okay, so let's review here. I've labeled the min terms. 0, 0, 0, 0, 0, 1 is 1. But remember, the third column had to be 1, 1, which is really min term 3. And 0, 1, 0 is min term 2. So the min terms go 0, 1, 2, 3. We've got to skip this column. 4, 1, 0, 0, 5, 1, 0, 1. We've got to skip this. Here's 6, 1, 1, 0, and 1, 1, 1 is 7. So if I fill these up, say, with these, then I can just label this as min term M0 or M2 or M5 or M7. And again, we'll use this shorthand, the sum of minterms 0, 2, 5, 7. So if I give you F equals sum of 0, 2, 5, 7, you can draw the Karnaugh map directly. Okay, let's look at 4-variable K-maps. It's just an extension where we'll have, say, W, X, Y, Z as the inputs. And now WX, this is W, this is X, so this is 0, 0 row. This is W0, X is 1, that's this row. And again, we have to make the third row 1, 1. So W1, Y is 1 is right here, and then W1, X is 0. So let's do an example. Let's label the minterms here. This is 0, 1. Remember, we got to skip this column. 2, 3, 4, 5, 6, 7. Now we got to skip the third row, so minterm 8, 1, 0, 0 is down here in the left corner. 8, 9, 10, 11, and then 12, 13, 14, 15. So you got to remember how these minterms are labeled, so that now if we write a function of W, X, Y, Z as the sum of all these minterms, this means you'd put a 1 in 2, 4, 5, 6, 7, 9, 13, 14, and 15. Let's do that and see how many circles we need. Can you see? Well, if we start with this outlier here, we can pick up all these 4. If we look at this one, it can only go there. If we look at this one, it can only go here. And now to pick up these 2, what do? Yeah, I include those other 2 and make this a 4 by 4. So we're going to have 4 terms here. What's this one going to be? This one is going to be not W and X, because Y and Z are going to go away. Not W and X. What about this one? This is going to be X and Y. X and Y. W goes away. Z goes away. How about this one up here? X goes away. We're left with not W and Y and not Z. Not W and Y and not Z. And finally this one. X goes away because it's 0 and 1. We're left with the 1 and the W, so it's W and not Y and Z. W and not Y and Z. So this 4 by 4 reduces to these 4 terms. Okay, let's look at one more example. How many circles do you think you need here? This is a little trickier one to think about. Well, to get this one, we can draw a circle here. To get this one, we need a circle here. Now what about these 4 corners we have here? Remember, I said this wraps around, so this one's really connected to this, but the top is also connected to the bottom. So actually these 4 corners are all connected to each other, and we can actually draw a 4 by 4 circle this way. So we're left with these 3 terms. What's this one? This one is going to be not W and Z. The X goes away, 0 and 1, and the Y goes away, 0 and 1. So we're left with not W and Z. How about this one? Well, we have W and X here, and Y, because the Z goes away. W and X and Y. And what do the 4 corners give us? Well, W goes away, we're left with not X. Y goes away, we're left with not Z. So this is just not X and not Z.